Okay, so this is a lecture from Chapter 9 on static equilibrium. And so for this, we have that in terms of the sum of the forces in the x direction will equal to 0. The sum of the forces in the y direction will be 0. And the sum of the torques will be equal to 0. So when an object is in true static equilibrium, it is not going anyplace. So in terms of how that works then, we can look in terms of this particular problem. And so I have an object that is suspended from two cables, and we want to find out what is the forces acting in each of the cables. My object here has a mass of 200 kilograms, and my angle here, theta, is at a 60-degree angle. So we want to know what is the forces acting on our two cables that is suspending this object. And so let's call this cable B. We will call this one cable A. And then there is going to be a downward force due to the weight of my block. And so again, for static equilibrium, the sum of the forces has to be equal to 0. And so the sum of the forces in the x direction has to equal 0. And for this particular problem, we will set up our axis in this fashion. So that would mean that going this way is in the positive direction on the x. Going this way is the negative direction on the x. So my forces in the x direction will be given by F sub B minus FA cosine of 60. And so that would be the x component of this applied force. Right? And then the sum of the forces in the y direction also has to equal 0. And so my y direction component is I have the y component due to this cable. This cable has nothing in the y direction, and then the weight of the block is also acting in the y direction. So the cable part here is acting in the positive direction, and so that'll be given by FA sine of 60 minus the weight of the block, which will be mg, and that will be 0. And so given that we know what the mass of the block is, we know what g is, we can figure out the force in cable A. And so FA sine 60 is going to equal mg, and then we can divide both sides by the sine. And so F sub A is going to be mg over the sine of 60. We have that the mass of the cable of the box is 200, g is 9.8, and the sine of 60. And we get that this force will be 2,263 newtons. Now that we know what A is, we can go back and we can now find the force in cable B. So from this one, now that we know A, we can find this one. And so based on that, we get F sub B will equal F sub A cosine of 60. So we get 2263 cosine of 60. And we plug that in, and we get that this cable is a force of 1,000 132 newtons. And so our object is not going to go anywhere. Right? So you want to hang up this sign, you go to Lowe's and you tell them you need 2 cables, one that can support a force of 2,263 newtons, the other one that can support a force of 1,132 newtons, and they'll probably give you a strange look because they'll have no idea what you're talking about. Okay. So in our next scenario, we'll look at what happens in terms of all these components, in terms of the X direction, Y direction, and what happens in terms of a torque. So, question like this. So where must the pivot point be? Placed in order to balance out two masses. So, and one is at each end. And so mass 1 is 70 kilograms. Mass 2 is 120 kilograms. Okay. And then also the board has a mass of 5 kilograms and is 8 meters long. Okay. So we want to figure out what's going to happen in this scenario in terms of where does that pivot point have to be so that system is totally balanced. So if we make a picture as to what is going on here, so basically we have our plank, we have our first mass, which we'll put here, so this will be in 1, and this one we said was going to be 70 kilograms, and then here we'll put mass 2, this one's 120 kilograms, and then somewhere there's going to be a pivot point for the system. We also know that the board itself has a mass of 5 kilograms and it is 8 meters long. Okay. So my two masses then, if I say that from here to here is given by X, then the distance from here to here will be given by L minus X, where L is the length of my board. So again, in static equilibrium, all the forces and the torques all must be 0. So if we first look what's happening in the X direction, we have that the sum of the forces in the X direction will be 0, and of course in terms of this whole scenario that is 0 because this thing is not moving in the X direction. So there is no motion in the X direction, and so we don't have to worry about this one. There is, however, going to be motion in terms of the Y direction and in terms of my torque. So in the Y direction, what's going on here? Well, we have the weight of this mass pulling down. We have the weight of this mass is pulling down. We have the weight of the entire plank is acting in the downward direction. And then all of that has to be balanced out by the normal force. And so in the Y direction, we have that the normal force will be positive. We have the mass of my first block times gravity. We have the mass of the second block times gravity. And we have the mass of the board, also times gravity, and that will be 0. Right? And again, before I go on any further, let's go back in terms of my axis system here we're using for this. And so for this again, we'll get y and x. And for torques, the way it works is that for torque, going this way is positive. And going in this direction is negative. So in this one, we can solve this for n in our normal force, and the normal force will be equal to just the entire weight of my system. And so this will be m1 plus m2 plus the mass of the board, all times gravity. So we have all our 3 numbers, and we can find the normal force for the system. So 70 plus 120 plus 5 times the 9.8. And so this comes out to be 1,911 newtons. Right? Right. So now we need to look and see what's happening in terms of the torque on my system. Right? So apparently there's going to be a pivot point here. And so the pivot point is going to be wherever this may be. And so you got that this side is going to want to come down. And this one is going to want to go up based on that pivot point. So we're going to have to look and observe what's happening here. Right? So, and again, the sum of the torques has to equal 0. And remember that torque was given by R times L, where R is the distance from the pivot point and F is the force. So we get M1 times G times X, X being the distance from the pivot point, which is my R value. We get for mass 2, M2 times G, L minus X. And then we also, because the board here does have a mass, it does come into play in terms of this whole torque. And so the board will be the mass of the board times gravity. And for the board itself, we look at it as a center. Where's the center of mass for my system? Right? So we get this. And so now we need to be able to take this equation and we need to solve it for x. So we have here m1 gx minus m2 sub g times L plus m2g times x minus mass of the board times gravity times L over 2 plus the mass of the board times gravity times x, and all of that equals 0. Well, you notice from this equation that G is common to every term, and so therefore the G will drop out, and so we can eliminate the G's. And we end up with this. And so now we want to take this equation, and again, we want to solve it for x, which means I want to keep everything that has an x over on this side, and everything that doesn't have an x, I want to take over to the other side of my equation. And so I can do that by bringing this to the other side, and bringing this to the other side, and whatever you do on one side of the equation, we have to do to the other side. And so over here, we're going to add M2L and the mass of the board, 2. And so when we do that, we end up that we get x and sub 2x mass of the board times x is going to equal M2 times L and the mass of the board. 2. So now, over here, x appears in every term, and so we can now take the x and we can factor that out. And so x, we get M1, M2 plus MB is going to equal all my stuff on the other side. Okay. That. And then over on this side, we could actually also factor out my L, and we end up with M1 plus M sub B over 2, all of that times L. Next step is to divide everything out and solve for x. So we divide everything by this side. This by that. And we end up that x is going to be M1 plus the mass of the board over 2 over M1 plus M2 plus M3, all of that times L. So now we can take and we can plug in our numbers. We know all the masses. And so and I think I made an error here. Back M2. That's an M2, sorry. That's a 2. Not very good in my correct that. So all of these should be 2s, right? So we have the mass of block 2, which is 120. The mass of the board, which is 5, so 5 over 2, over the combined masses of my entire system, so 70 plus 120 plus 5, and all of that times the board length, which is 8. And we plug all that in, and this basically will come out to be 5 meters. So we know where the pivot point has to be for my system. So it needs to be, in terms of the system, it needs to be 5 meters. Right? And so we go back to my drawing here. We got that makes sense with what we know, because we know that the center of mass is going to be, that pivot point will have to be closer to my heavier mass. Okay? And so it'll be 5 meters from here, and so only 3 meters from my heavier mass. Okay? So we found the pivot point needed for the system. Okay? So another question involving torque, and so now you've got here in terms of a sign suspended here from a board and a hinge here, and then we have this wire attached at this point. And so again, we want to find out here is what is the tension going to be in terms of my wire in the system. Right? So again, using the same axes we've been using in terms of my directions, and so let's set up a system here. And so for this, we're going to let L1, length 1, be the 1.7 meters, so that'll be the entire length of my plank. L sub 2 is going to be the length out to where the guide wire attaches to this. And then in terms of the center mass for this thing, that would be the total length divided by 2, and so that would be 0.85 meters. Now in this problem, they actually told you the weight of the system, of each item. And so remember that newtons is actually a measurement of weight in physics. And so we'll have that M1G is going to be the 155 newtons. So that will be the weight of the beam. And then M2G will then be the weight of the sign, which is 245. Okay. And again, we want to find out what's happening here in terms of our system, and we want to find out what is the tension in the wire for this particular setup. Okay. So again, the sum of the torques has to be equal to 0. And so we had before that when we talked about torque, we talked in terms of R times F. And this particular one, we will use the more general equation, which is RF sine of theta. Okay? So for the Planck question and the balancing point, my forces were acting at a 90-degree angle, and so sine theta went away. In this case, we now have that my wire is going to be acting at a 35-degree angle here. So we need to take that into account. Okay. So we got that the tension in the wire times sine theta is going to equal times L2, so that'll be my torque due to my wire, okay, minus M1 times G L over 2 minus M2 times G plus 1. Okay. So in terms of the actual beam and my sine, they are acting at a 90-degree angle, and so sine theta, sine of 90 is 1, and so that part goes away. And so we want to solve this for F sub t. So really we want to solve this for the tension in the wire. And so I can take these two terms over to the other side, and I do that by adding. And so whatever I do on one side, we have to do on the other side. Okay. And M2 G. And so we get Ft sine theta L over 2 is going to equal M1 G L over 2 plus M2 G L sub 1. Again, we want to solve for Ft. All of this is multiplying. And so the opposite of multiplying is to divide. So we divide both sides by L2 sine theta. And we get that the tension in the wire is going to be given by M1G L over 2 over one in here, so that should be L sub 1. And let's stick that back in there. Alright. So now we have all our numbers, and so we can just take our numbers and we can plug in, and we get the tension here acting in my wire. M1G, again, mass times gravity is weight, which is what they actually gave us in this particular problem. And so we get 155 times 0.85 plus 245 times 1.7 all over 1.35 times the sine of 35. And we plug that all in, and we find out that the tension in the wire in this case will be 708 newtons. Okay? So we now have what that wire has to be. We can also look in terms of this one, in terms of what are the forces acting in the x and in the y direction. Here. So my hinge has got an x component. So we go back to my drawing. Here's my hinge. This is F sub h. This was F sub t. Okay. There is an x component to this force. There's an x component to the tension in the wire. There also are y components for each of those. So we go in terms of what's going on in the x direction. Again, the sum of the forces in the x direction has to be equal to 0, and so the force of the hinge in the x direction is in the positive, will be equal to the tension in the wire and the cosine times the cosine of the angle. So the x component of that tension in my wire, and so we get F h sub x is going to equal the tension in the wire times the cosine of the angle. We know F sub t, we know the angle. So we get 708 cosine of 35, and we find out that this number will be 580. Now we can also look in terms of the y component due to my hinge. And so, again, the sum of the forces in the y direction has to equal 0. So sum of the forces in the y direction has to equal 0. And so we have the force of the hinge in the y direction. Okay. We have the upward component due to the tension in the wire. Okay. We have my two weights, which are acting in the downward direction. So the weight of the beam and the weight of the sine are both acting in the negative direction. And so again, we know all the numbers here, and so we can actually solve for this. And so again, the way I do that is by doing the opposite operation, and so we get that the force of the hinge in the y direction will be given by m1g, m2g, minus ft sine theta. And so m1g was the 155, m2g was the 245, and then this would be 708 times the sine of 35. And so we find out that the force here ends up being a negative 6 newtons, which means that the force is acting in a downward direction. Again, positive and negative are indications of direction here. So we have in terms of static equilibrium here, and that the sum of the forces in the x direction will be 0, the sum of the forces in the y direction will be 0, and the sum of the torques will be 0. Okay. So then in terms of systems, we can look in terms of the materials that are used. And so you get in terms of elasticity. And so we get that the force is given by K times the change in the length, and K is from Hooke's law, is that component of how much force is needed in order to cause something to stretch. And so you get in terms of this diagram, in that if we apply a force to a piece of metal and we start pulling on it, for a while it will stretch and be able to return back to its state. And then you get to a point that a little bit more of applied force and it'll just give and stretches. And then if we apply too much force, we get to the point where the whole thing just breaks. Okay? And so we can find this by using in terms of Young's modulus. And so we get this equation. And so in terms of what everything stands for here, we've got delta L is going to be the change in length. E is a constant, and it is Young's modulus, and they give a table in the book for these values. F is the applied force. A is the cross-sectional area. And then L naught is what was the initial length. So really, if we have a steel beam or whatever, we can look at how much force is applied to it, and we know the cross-sectional area. We can see how much will it stretch given that. And so you get in terms of this equation. Now, unfortunately, when I copy this from the book onto this page of the Smart Notebook, where you see 100 times 109, it actually should be 100 times 10 to the 9. So all of these 9s here should be exponents. Not the way it came out. Okay. So we can use this information and we can solve the problem. Right? And so we can look at something like this. So how much does a steel wire stretch when a 50,000 Newton force is applied given it has a diameter of 1 centimeter and is 5 meters long. So we want to know how much will this stretch, and we can find this out by using the equation we just had on the previous page. And so first off, we need to make sure that all the units are correct, and so we need this. This is the diameter, which was 1 centimeter. So diameter is 1 centimeter, which of course would be 0.01 meters. But again, from my equation, we need to know cross-sectional area. And so this is a circle. And we know that the formula for area of a circle is given by pi r squared. And so I don't want to know the diameter of my wire. I want to know the radius of the wire. And the radius here will be 0.005 meters. So now we have it in terms of what we need in order to go ahead and solve this particular problem. And so we can plug into that equation, and so delta L is going to equal 1 over E, and that number from the book is 200 times 10 to the 9 times the force, which was 50,000, over the cross-sectional area, which is going to be given by pi r squared, so that'll be pi times 0.005 squared times my original length, which was times my original length, which was 5. Actually, let me change this. Actually, my question I have written down. Sorry, but this number should be a 3. So let's make this match. Right. So this will be 3, and so we can plug that in, and we can get the change in length for this piece of wire. And so it ends up that this wire is going to stretch by will stretch by 0.0095 meters. So it's not going to give very much, and we don't want that to happen in terms of our steel wire. Okay? Well, we can also look in terms of this wire and what's happening to it. We can look at a couple other quantities, and that is in regards to stress and strain. And so stress is given to be the amount of force per unit area. Okay? So in the case of this particular problem, then, we got that the applied force was 50,000 newtons. The area, again, was given by pi times 0.005 squared. And we get that the stress on our system here ends up being 636619772 newtons per meter. And then we can also look in terms of the strain on our system, and the strain then is given by the change in length over the original length. And so this number will have no unit, it's just going to be a ratio. And so here we get 0.0095 divided by 3, and this comes out to be 0.0032. So that number is just the ratio as to what's going on. Okay? So we have in terms of stress, strain, and figure out the change in length of a piece of wire. Go. We can also look in terms of types of strengths. And so types of strengths are given in terms of three things. So the three types we have in terms of tensile strength, so basically pulling on either end, compression, so pushing down, and shear, which is basically a twisting of our system. Okay? And so again, there is a table in your book that gives you the values for different types of things, and that one did not copy very well, so you won't see it here up on the board. Okay? But in terms of problems dealing with this type of stuff, we can look in terms of something like this. So we want to use a bolt, connect two plates, want to stand a force of 3,200, and basically we had a safety factor here, which is what that 6.0 is, basically how strong we want this system to be. And so in terms of formula for this, we get that the shear strength, which again is a constant, which you can find in tables, divided by the safety factor, is going to equal the force over the area. So in this particular problem, we want to know basically in terms of the wire, how good of a wire do we have to buy in order to do this? Right? So we can take this equation and we can solve this for A. Again, it's a proportion. And the way we solve a proportion is to cross multiply and divide. And so we solve this for A. We get A is going to be given by the safety factor times the force divided by the shear strength. And so we can have all the numbers. This number comes out of a table. And so we get that this will be 6 times 3,200 divided by the strength, which is 170 times 10 to the 6. And we get that the cross-sectional area here will be 0.00011 meters squared. Okay. Now, the question you want to know, however, is in terms of the actual wire, what is the diameter of that wire? Well, we know the area. We know that area is given by pi r squared. So we can take this equation and solve this for r. And so we get that r will be the square root of A divided by pi. So we get r is going to be the square root of 0.00011 over pi. And so the radius of my wire is going to be 0.006 meters. And the question wanted to know in terms of the diameter. And so the diameter is going to be twice the radius, and so you get 0.012 meters. And with that, that will conclude the discussion on Chapter 9. Thank you.